Okay, so for our final installment for the greenhouse environment course, I wanted to do a little bit of review on the phytochrome response and also do a couple of climate scenarios to prepare you for your final exam. And maybe get you started thinking about managing climates so that when you take your course next winter, this coming winter with Matt or in greenhouse controls, you'll do a lot more scenarios and this will kind of get you off on a good start. So yes, this is my hybrid Star Trek, Star Wars silly thing that it really has nothing to do with phytochrome, but I don't know. At the time, it seemed funny. Um, just as a review, the phytochrome response has to do with this molecule phytochrome, which can change to two different configurations, and the molecule just keeps flipping back and forth depending on what light is currently hitting it. So in the PR, it is the R denotes the sensitivity, right? So when it's in a PFR state, right? So this state, that means it's sensitive to far red, which means when far red hits it, it will convert to a red sensitive form. And it just flips back and forth like a light switch. So whatever state it's in is the color it's waiting to see, right? So we're talking about 730 nanometers, which is far red, means that the PFR will see that color. And when it's 660 nanometers, that means that's the color that it's looking for in the PR state. Okay, what does all this mean? Well, there are obviously responses that plants will that they have an impact on plants, right? We've talked a lot about this. You should have talked about this in Plant Science 1. I'm kind of reviewing it because I'm finding students are a little confused on it. One last note before I leave this slide, and that is that phytochrome slowly turns back to the PR state in the dark. So if you expose the plant to far red and it goes to the PR state, that's fine, but it also will slowly go back to the PR state in the dark. This is part of the sort of circadian rhythm of measuring nighttime. So what are the list of things that happen from phytochrome? This is kind of why we're talking about this, because it's fairly extensive. Germination being a very big one, right? So something called photodormancy. Stretch, we've talked a lot about this term. Flowering, you've talked a lot about in Plant Science 1. De-etiolation is another one, and hypocaudal hook straightening, and then of course unrolling of leaves. These last three are maybe less obvious, although I'm sure you've seen de-etiolation happen yourself. So the relevant to sort of seeding for bedding plants happening in the early next term, one of the things that's important is seed depth. So it depends on the seed. Not a lot of seeds, actually a fair number of seeds are fairly forgiving, but some are actually very picky about the depth that they're seeded at. Like you'll notice some you lay the seed on the surface of the soil and others you bury. And there is a limit of light penetration into soil where far red light just can't penetrate anymore, and seeds that are planted below that will not germinate. And in some cases, the seeds don't want to see far red; they want to see more red, and they're the ones that you lay on the surface of the soil, so that their red ratio to far red is such that the seed knows that it's on top of the soil. It's all about the seed knowing when it's in the right circumstances for germination. Lettuce seeds like some light, some red light to germinate, so they're often near the surface, or not buried at least, as an example. Shade response, we spent a lot of time talking about that. The idea that when one plant is overlapping another, it reflects red light, right? So the red light doesn't make it through, but the far red is able to pass through the leaf to leaves below, shifting the phytochrome response in the leaves that are underneath, which means that the plant, this plant in this case, this plant, which is being shaded by this plant, will cause it to stretch because it will be in a PR state, it's phytochrome, which triggers the release of things like gibberellic acid, causing cells to stretch. uh, so that this plant will become taller, so that it's competing with its neighbor for light. It's all about competition, right? One giant competition. So this is where we talked about PR to PFR or PR to PFR in the sense that the PR state is more dominant, which means it stretches. At the end of the day, and we've talked a lot about this, it's about far red light, right? So in the beginning and the end of the day, when there's more far red in the spectrum, for example, or just in the sense that, you know, the kind of lights you're using or the density of your crop, which is probably the most common, right? This is the most common example of where phytochrome response is detrimental to the quality. Like poinsettias, we talked about stovepiping, where the plants are put on too high density in the bench. This is exactly what's happening there. Some more pictures just to show you, I think this is a Arabidopsis with high red light and low red light in the spectrum. And you see the response is massive stretch. Interestingly, when we were talking about LEDs and HPS lights in that one paper review, and then with a few students on the side, I mentioned that LED lights are really good for propagation benches. And one of the reasons being is that we can play with this red ratio and keep young plants and cuttings very compact, which is beneficial commercially. Flowering. Again, Plant Science 1, you would have seen this. I just want to make sure we review that. This night interruption, splitting the night into 2 short nights so that the plant thinks that it's a short night. Some of the research that was done on this with phytochrome showed when they did a flash of red light, for example. So in a short day plant, it's expecting a long night, right? So if you do a flash in the middle of the night, it's going to inhibit flowering. But when you did a far red flash, it actually reset the phytochrome, so it canceled that perceived night light, and it in fact thought it was a long night. So far red will also negate your interventions for controlling flowering. So if you're growing mums, for example, right, we know we need a long night for them to flower. And of course, if we want them to stay in a vegetative state, we're going to turn on lights in the middle of the night. That's this red. We're going to turn on the lights. And if you remember from one of the other lessons, all you need is incandescent bulbs to do this. You don't need a lot of light, just a little bit of red light to impact the photoperiod. So hanging little bulbs, which of course have to have red in order to work because we're dealing with phytochrome, that small amount of light is enough to stop the mums from flowering. And of course, if you ended up with a far red flash in the middle of the night, it would negate that and it would still think it's a long night. So far red, and of course they went nuts and did red, far red, red, far red, red, far red, and of course it just kept flipping the switch in that research. Deadiolation. This is where seedlings that don't have enough light actually don't grow. They don't develop chlorophyll and they look yellow. In some instances, this is desirable. Like, for example, some grass and corn greens or seedlings are germinated for nutritional purposes, and they will purposely grow them in the dark to make them yellow. And they have a sweeter taste, mainly because chlorophyll is not being developed and the sugars move up from the roots and fill the cells. It's not great from a growing perspective, but it has been used. But far red light is what triggers deadiolation. And then, of course, pea shoots, really extreme example of where there's an absence of far red, you get deadiolated growth. So it thinks it's underneath the ground still, and it keeps pushing up, thinking sooner or later I'll get to the top of the soil and I'll start growing my leaves and chlorophyll. So that's a far red response. Hypocotyl hook straightening. This is when seedlings are germinating. The idea is that the hypocotyl hooks so that as it's pushing through the soil, the delicate leaves and meristem are not damaged. They get dragged behind upside down so that they're not peeled off. And then as soon as this hypocotyl sees light or sees red light, it actually straightens out. And then the leaves unfurl. So that is yet another phytochrome response. And then lastly, unfurling of monocot leaves. So, for example, when corn germinates, the coleoptile emerges. Same with all grasses, right? It emerges sort of as a tight coil, and when it sees red light, it unfurls its leaf. Sort of think of it as a tube unrolling into a flat leaf. So that's just a summary of the phytochrome response. Just want to make sure that goes properly covered before you head off into the next term. For the second part of this lesson, I wanted to sort of do some climate interaction scenarios. So looking at things like light, humidity, and temperature, and how they work together. And again, we have talked about this, but I want to absolutely make sure we're all on the same page and clear on how this all works. Powdery mildew, this is a scanning electron micrograph over here of powdery mildew on the surface of a leaf. It grows on the surface and it basically extracts nutrients from the leaves. The hyphae penetrate the epidermis, and then the powdery mildew just starts sucking sugars out of the leaf. That's why leaves often look yellow where the powdery mildew is growing. Some people have said, well, you know, the powdery mildew is not on my fruit, so it doesn't matter. Well, yes, it does, because it's saprophytic on the sugars. It's sucking up the sugars of the plant, which means there's less sugars for your fruit, which means your yields are impacted. So powdery mildew is never a good thing, not to mention inhaling spores for staph and stuff like that. I've seen some cucumber houses that get pretty gross. That's just not really a great environment. So to clarify, it germinates at high humidity. So the spores germinate and establish a foothold. All right, they start to grow. But when you have really, really low humidity, it actually forms spores and spreads. So your worst case scenario is to have an environment that's oscillating between high humidity, low humidity, high humidity, low humidity, because you're just going to spread the disease all over the place. Another interesting note about powdery mildew is that very high temperatures kill it. So I have seen some greenhouses, cucumber houses, run their temperature up to higher than 35 degrees Celsius for a couple hours, and it actually kills powdery mildew. Just cleans the whole place up instantly. Now, obviously, it doesn't disappear. Anything that's already established doesn't disappear, but on new growth, you don't see it anymore. All right, then we're looking at an ideal range of 70 to 80% humidity is where we want to watch that our plants are in that range for a number of reasons, not just for powdery mildew, but for transpiration, so that the plant's not stressed, but there's sufficient transpiration. Why do we want to watch temperatures at the same time, right? Well, again, reviewing this, the idea that water in air, this is just grams of water that are in the air, changes as water goes up. It's exponential. So as the temperature of your air increases from 10 to 20 to 30 degrees Celsius, it's able to go anywhere from, say, 8 grams per kilogram of air all the way up to 28 grams per kilogram of air, just because the temperature, it's non-linear, so it increases with temperature. To put it another way, this is vapor pressure as a percentage of air. So as the temperature increases, the vapor pressure increases. Probably the best way to portray this is with this graph, and this is the one I like the most, because what you see here is if I take a fixed volume of air, so this is, imagine a sealed chamber of air, okay? And I drop the temperature, right? So I lower the temperature in the morning. What happens to my relative humidity? My relative humidity goes up. And as the air temperature increases, my relative humidity goes down, because the air's ability to hold moisture changes or its vapor pressure changes. So this is really important from a greenhouse, because the greenhouse essentially, if you think of it, not that it's sealed, but think of it as a sealed box. Your relative humidity oscillates depending on temperature. And if you're trying to manage disease, right, this is where we have to be extra careful to monitor as our temperatures change, which of course they do all day. As the temperature changes, we have to monitor humidity. And the classic example is the end of the day. The sun is going down. There's less solar energy hitting the greenhouse. Temperatures start to cool. As the moisture from all the plants having transpired and grown all day, that moisture is in the air, and the greenhouse temperature is now starting to cool. What happens to relative humidity? It starts to increase, and it starts to get into the danger zone. Now, these temperatures and humidities here, this is just a climate graph. It's not maybe relevant to our crops because, look, it's cold. They're looking at 4 to 10 degrees Celsius. But in a greenhouse context, this is exactly what happens all the time. And when you have powdery mildew problems, it's because you're not properly managing your humidity as it relates to temperature. So linking that back to vapor pressure deficit, the green zones on this chart, this is taken from a Argus computer controls. The green zone is the zone where plants are happiest. So here we have, in this range, plants are transpiring properly. If we end up with too high humidity over here, the rate of transpiration slows. And as the humidity lowers and our vapor pressure increases a lot, our plants stress out and actually begin to close their stomata and reduce their overall transpiration. So we want to make sure the plants are in this happy zone for optimal growth, right? That's why vapor pressure deficit is so useful for a greenhouse context, because it factors in both humidity and temperature from a plant's perspective. But it does not manage disease, because if you're snapping in your relative humidity, there are scenarios where you can have perfectly acceptable VPD, but look at your humidity is in 90 to 85%. And you can also have a perfectly acceptable VPD, but your humidity is extremely dry. So in this case, you're sporulating, and in this place here you're growing your powdery mildew. So even though you're not locking in your VPD in these ranges, you're not managing disease. So I've got a few scenarios to go over with you, and then we'll call it a term, and I'll post some review questions, and then you'll have your online exam next week as scheduled for your class for that whole day. But I'll have announcements that sort it all out just in case you're wondering. So here, each slide coming up gives us both the light that the greenhouse is seeing throughout the day, the temperature, the vapor pressure deficit, and the relative humidity. Okay? So in this scenario, which is a sort of a happy normal day, the sun comes up in the morning, it peaks at lunch, and then it starts to go down for the afternoon, and then it's gone for the night. This is a normal, nice, sunny day. Right? So as we can expect, the temperature in the greenhouse is going to increase as well, and then slowly decrease as the sun gets lower in the sky. And of course, at the same time, because the plants are transpiring, we're going to also have increased temperature. We have a vapor pressure deficit transpiring along with it, as the temperature being the bigger factor, right? As it gets warm, our air can hold that much more moisture, so the vapor pressure deficit increases. Or the opposite, if you want to look at it, basically as the temperature gets warmer, right? As the temperature gets warmer in the middle of the day, our humidity drops because the air can hold more moisture, right? So remember, the plants are still transpiring. That's okay. We're probably venting at this time, but the relative humidity goes down because the greenhouse is so warm. So let's look at some scenarios outside the normal sunny day. In this case, the sun came up, it peaked, and then it got cloudy. So starting around 10 o'clock in the morning, clouds rolled in, so the sunlight disappeared. And you look at the temperature, of course, the temperature went up as the sun was going, and then when the clouds came in, the temperature just plummeted uh, and dropped and then eventually recovered. So what does that mean for the vapor pressure deficit? Well, the VPD increased as the temperature got warm, and then when the clouds rolled in, the vapor pressure deficit dropped, and transpiration began to slow. Now remember, the ideal range is around 6 and up. So it would be safe to say that the plants were not doing a lot of transpiring here and not a lot of transpiring here. So we have a situation where little growth happened that day because there was not a lot of movement through the vasculature of the plant. Not to mention there wasn't a lot of sun from 10 o'clock on, right? Looking at humidity, we have a situation where it started the day rather high at 90%, and as the sun came up, the air warmed, it started to be able to hold more moisture, so the relative humidity dropped and dropped and dropped, hit 70, and then started to come back up a little bit as things cooled. But for the most part, the 70 to 80 zone of happiness for powdery mildew was only enjoyed for a small part of the day. In other words, it's too humid here and it's too humid here. So this is a disease that is prone to this is a climate, sorry, that's prone to powdery mildew, and it's not being is being poorly managed. So what would we do here? Well, at this point, the clouds came in. Most likely the boiler should have kicked in to maintain the temperature in the greenhouse instead of letting it dip and then turning the boilers on and recovering late in the day. So here we have a situation where we were too slow to react from the climate, and not to mention we started the day with high humidity, so we probably should have had the vents on and some heat on, or maintained a warmer temperature, although at 18 degrees is not that bad for overnight. So my guess is that vents should have been open. So this farmer was being cheap and didn't want to let heat out, and of course started the day with high humidity. So we're talking powdery mildew here. Let's look at another scenario. This is a dark day, so not a lot of sunlight. So the sun got up to only 100 and maybe 200 watts. Temperature started the day cold and barely made it over 18 at the middle of the day. There's no clouds rolling in here. It's just generally a dark day. Maybe it was cloudy the entire day, let's say. Vapor pressure deficit barely made it into the green zone. So it's high humidity. There's not a lot of transpiration happening here. Very little growth happened this day. And we look at relative humidity. Where's our 70 to 80 zone? The entire time, almost the entire day, we were in high humidity situations. So again, powdery mildew all over the place in this scenario. This is not ideal climate management for growth. Now, not everyone has grow lights, right? If you had grow lights, you could have bumped the light up and then had the temperature higher, and you may have been taking this graph and started more like this and had the plants growing all day. And maybe you would have driven your RH down to this area. Hard to say, but in this situation, this is a really good example to show where supplemental lighting makes a big difference, because not a lot of growth happened this day. There's very little transpiration happening, and you have disease scenario for, basically there's only 4 hours of the day where you're not in a disease inducing environment. So again, not a great what we call active environment. Let's look at this last one. So here we got a really bright day. We're hitting 1500 watts. This is really sunny. We're getting into a hot summer day. This is not midwinter. Look at the temperature. 31 degrees Celsius here. We hit 37, 38 degrees Celsius max for the day. This is very, very hot. Let's look at the vapor pressure deficit. It starts active, nice active environment, and then it starts getting into the danger zone. And for this part of the day, so from 9 o'clock until 4 o'clock, that's a long time. the plants are so stressed because vapor pressure deficit is so high that their stomata are likely closed, right? So the stomata are closed, so zero transpiration is happening. And on top of that, because of the temperature, like we're looking at a temperature in excess of 31 degrees Celsius, the plants are not cooling because A, they're not transpiring, so there's no evaporative cooling, and you have high temperatures, which means the leaf temperature is probably skyrocketing. And the plant's respiration rates are so high that the plant's consuming sugars that it probably built up for the previous 2-3 days. This is a really bad day. We have some severe stress on the crop. It's not active, the stomata are closed, the leaves are overheating, and respiration is through the roof. The only positive thing about this day is that, hey, look at that, we're in the 70-80 zone, so there's no powdery mildew, but what does it matter if your crop is basically suffocating to death? So in this situation, it would have been better to close the curtains, to shade the greenhouse, right? To bring that radiation energy down, to block the light so that it's reflected off the greenhouse, which would have kept the greenhouse probably below 31 degrees Celsius, which would have allowed us to have the vapor pressure deficit shifted downwards. Likely in the middle of the day, it still would have gotten up a little bit higher, but that's okay. You can handle a couple hours of stress in the summer. And our humidity likely would have stayed similar or been slightly higher, but you can manage that with ventilation, right? So this is a situation where energy curtains or shade curtains most definitely should have been used and would have been very helpful. All right, so I hope this gives you a good introduction of how sort of light, temperature, and humidity interplay to create what we call an active growing environment. You're going to talk more about this next term, but like I said, I wanted to introduce you to this concept this term. All right, I wish you all the best of luck on your exams. Check that you've got your quizzes all done and your paper reviews handed in, and you'll be just fine for this term. I think everyone in the course seems to be doing well, so I'm happy. All right, I will see you in the winter. Have a great Christmas. Take care. Bye.